Hey everyone, and welcome. Today we are going to crack the code on some super important math concepts, systems of equations, and geometric transformations. And hey, before we start, don't forget to like and subscribe at @Loka26M for more lessons on math and other subjects. All right, let's begin. We're going to break this all down so it's clear, quick, and maybe even a little bit fun.
So, check this out. At first glance, it's just two lines crossing on a graph, but it's so much more than that. I want you to think of each line as its own unique path, its own story. That one spot where they cross, that's the one single point where both of those stories are true at the exact same time. That's our solution. It's literally the X that marks the spot.
All right, so let's dive into our first big idea. When we talk about solving a system of equations, what we're really asking is, how do these lines hang out together on the graph? Do they meet? And if they do, how many times? Turns out, there are only 3 ways this can go down.
Okay, so this is the one you're going to see most of the time. The lines cross at exactly one spot. And when you've got the graph right in front of you, finding the solution is a piece of cake. We just follow the lines to where they meet. For this one, we go over 1 on the x-axis and up 3 on the y-axis. Boom, the solution is 1, 3. One intersection, one solution. Simple as that.
Now, what about these? These guys look just like railroad tracks, don't they? That's because they're parallel. They have the exact same steepness, or what we call slope, so they're going to run side by side forever, but they will never ever cross. When you see this, it means there is no solution. There's no point in the universe where both of their stories match up.
And here we have the sneakiest one of all. What if, and this is kind of tricky, what if you have 2 equations that look different, but they're really just the same line wearing a disguise? When you graph them, you just get one line right on top of the other. So what's the solution? Well, every single point on that line is a shared point. That means there are infinitely many solutions.
Graphing is awesome when you can see the picture, but what happens when you don't have that map? That's where a little algebra comes to the rescue. Think of these next 2 methods, substitution and elimination, as the special tools a detective uses to solve the case without even needing to see the crime scene.
All right, let's take a look at this puzzle here. We've got 2 equations, but one of them gives us a massive clue. It flat out tells us what y is. It says y is the exact same thing as 2x. We're going to use that little secret to crack this whole system wide open with a method called substitution.
Okay, so here's the game plan for substitution. Since we know y is 2x, we can literally just swap out the y in that first equation for 2x. It's like we're setting it undercover. So now we have 5x minus 2 times 2x equals 3. Let's clean that up. 5x minus 4x is just x. So x equals 3. Case cracked. But wait, we need its partner. We just plug our new value, x equals 3, back into that first clue, y equals 2x. So y equals 2 times 3, which is 6. Our full solution is 3, 6.
All right, time for our next tool, elimination. Take a close look at this one. This problem is set up perfectly for a whole different kind of trick. I want you to look really closely at the y terms. Do you spot the shortcut? What's the very first thing that jumps out at you?
You got it. We have a positive 3y and a negative 3y. They're perfect opposites, just waiting to be canceled out. If we just add these 2 equations together, straight down like an addition problem, that plus 3y and negative 3y will completely eliminate each other. Poof! Gone. And that, my friends, is the magic of elimination. You spot the opposites, you add them up, and they vanish. All right, let's totally switch gears. We've been busy tracking where lines meet, but now let's talk about how shapes move. So welcome to the world of geometric transformations. These are basically the power moves for any shape on the grid. We're talking slides, flips, and turns. So here we've got a classic before and after. We start with our OG triangle, ABC, and it moves to this new spot and becomes triangle A', B', C'. Our job is to be the detective and describe exactly how it made that journey. This kind of move, just a simple slide, has a special name, a translation.
So how do we crack this code? It's actually super simple. All we have to do is pick one point and follow its journey from start to finish. Let's use point A. It starts at -6, 1 and lands at A', which is at -2, -8. Okay, let's count it out. To get from -6 to -2 on the x-axis, you have to move 4 units to the right. And to get from 1 all the way down to -8 on the y-axis, you have to move 9 units down. And that's our rule. Right 4, down 9.
Okay, let's talk rotations or turns. These have some really specific rules, but they're easy once you know them. A 180-degree rotation is like taking the shape and spinning it halfway around the center point. And the rule for this one? So simple. The coordinates just flip to their opposites. So any point xy becomes negative x, negative y. It's like a secret code.
Now, a reflection is just a flip. Think about looking in a mirror. If we reflect a shape over that vertical y-axis, it's going to flip horizontally. The up and down part, the y-coordinate, doesn't change at all, but the left and right part, the x-coordinate, flips to its exact opposite. So the rule is x, y becomes negative x, y.
All right, you've learned the moves, you know how to slide, you know how to turn, and you know how to flip. So now, let's put it all together for the Master Challenge, where we combine these ideas into one big puzzle.
Okay, check this out. Our starting triangle, ABC, has a long way to go to get to its final spot, A double prime, B double prime, C double prime. This wasn't just one simple move, was it? Nope, this is a two-step journey. We call this a sequence of transformations. So, what do you think happened first?
So, let's play detective. What are the clues? Well, the final triangle isn't just slid over, it's also pointing the other way. It's a mirror image. So that means the first move had to be a reflection, a flip across that y-axis. That gets it to the other side of the grid. And from there, it makes its second move, a simple translation, just sliding straight down to its final destination. A flip, then a slide.
And just like that, we're through. We have covered a ton of ground today. I want you to think of everything we just went over as awesome new tools that you've just added to your personal math toolkit. Let's do a quick review to make sure they're locked in. So, let's do a super quick rundown of the big ideas. For systems, the solution is just where the lines cross. You can have one solution, no solution if they're parallel, or infinite solutions if it's the same line. And you can solve them by graphing, using substitution to swap a variable, or elimination to cancel out opposites. For transformations, remember the moves. Translations are slides, reflections are flips, and rotations are turns.
So you might be thinking, okay, that's cool, but why does this actually matter? Well, think about it. The GPS on your phone is constantly solving systems to figure out exactly where you are. Every single character in your favorite video game is being translated, rotated, and reflected all over the screen. This stuff isn't just in a textbook. It's the code that makes our world work. So my question for you is, what are you going to build with your new toolkit?